Maxwell bringing the last time I think we get to the form of the solution for E and B, right? And wait, we went to 651, 652, right? And so this is from the solution of the solution for the wave equation for E and B. This is basically taking the derivative of the wave equation for phi and A and whatever the right hand side, put it in exactly the same integral, the green function. That's 651 and 52. And last time when we mentioned this result, we just point out that you need to be a little careful about taking the derivative. Right now, the derivatives of whatever the respect, especially the gradient pi of the rho. This is inside the bracket. When you take the derivative with respect to x pi, it's not doesn't work on the x pi where you eventually substitute using the retarded bracket. Retarded bracket means whatever we t pi inside the function, inside the bracket, we change it to t minus r over c. R has this R has its absolute value x minus x pi, the distance between x and x pi. So, but this gradient only work on the original x pi dependent, not the x pi in the after you do the retarded bracket. So there's an order. So you take the derivative first, then you take the retarded bracket. The order is important. So last time we followed, and you can actually work out explicitly how you can also move this gradient outside the bracket. Then you divide another set equation 655 is 56. Actually, the one more if you apply, if you take the t pi derivative outside also, then you get use 6.57. You do that. That is actually trivial. But if you do that, then you get another set of so another form of E and B. So this is the form that with the derivative inside the retarded bracket, which is actually fine when you're doing calculate as long as that can be done. But alternatively, you sometimes for another purpose, it might be easier to take the derivative out first before you take the take the retarded first before you take the derivative, or then take the derivative and then take the retarded. So that one important application is applying to a point charge. So you need, when you apply, you try to derive a point charge, the formula for a point charge, field solution for the point charge, and it's easier to move all the derivative outside the bracket first. Okay, so to do that, we just need to be a little careful. And Jackson wrote down those formulas, and to derive the formula, actually just some careful consideration of taking derivatives. So we can start by, let's see, work on this one. The time is trivial. We'll do that later. So this one you have a derivative inside, but we can work on the outside first. So rho is a function of x prime t prime, right? If you take retarded bracket, this means this whenever you see x prime, whenever you see t prime become t minus this thing between x and x prime divided by c. Okay, that bracket actually just like that, right? And so if you have taken a gradient pi of this guy, so this is different from this one. This is outside, and which means because there's x prime here, x prime there. So basically, you need to take the derivative with respect to both of these x prime dependency. So the first one is taking the derivative over the first argument is actually exactly like this. It's just what we said, that taking the rho gradient pi of rho, then take the retarded. That is the first term in taking this derivative and operate on the first argument. Then the second term will be operate on the second argument, which has this dependence originally is t pi. You just substitute t minus this distance divided by c into t pi. So this derivative, you can say this is this slot is for t pi. So basically, you want to do the t prime derivative first. So you want to do a t prime partial rho partial t prime. But that would be taken derivative of rho with respect to the second argument. Then you use the chain rule. Then you do the derivative over the argument, and then the derivative is over x prime. So t doesn't have x prime, so that's fine. So you're taking just the second term of the second argument. So that would be a minus, and taking the gradient of this x minus x prime, right? And you know how to do the arc. You know how to do that? It's minus taking a derivative of the distance with respect to one of the vectors. You remember that? Yeah, it's just this is just like the coordinate, right? Then if you take a gradient, just like the radial unit vector, if you take the gradient of the unit vector, what do you get? Gradient of the coordinate, basically. If you the usual coordinate, the spherical coordinate gradient, or what is gradient? We talked about that before. Using in spherical coordinate. One in what unit vector? It's a vector. Gradient is a vector. The unit vector. Yeah, the unit vector of, right. That's basically that is it. So yeah, minus sign and then unit vector in the x prime coordinates. So x prime minus x divided by minus x prime. So basically the reverse of that. Well, you can use the minus sign to reverse that also. So it becomes a unit vector of x minus x prime. Because this is a derivative with respect to the prime coordinate. So this is a unit vector of prime coordinate. Okay, and then that's it. And then all the t prime is still in here, so put it in the retarded. Okay. And now you can get Jackson's formula by reversing the order. And reverse. So this one, the right hand side, this one is equal to this one, and then minus this one. because like I said, we can change that to positive x minus x prime. This will be your Jackson's R cap, R unit vector, capital R unit vector, move vector reality. So this is the 6.50. Okay, so we divide that by this consideration, basically just careful consideration of derivative, right? Then the same thing happened. So you will take a curl of J, then obviously it's the same consideration. You can move it inside because now this has also two arguments. So you move the inside means you only work on this first argument. So pi rho J inside without the bracket. And then the second one is you have this partial P, partial J partial T. And then work on the derivative over the argument T pi, right? And so you work on I mean, this is now a J function. It's a vector function, and you take the curl of that, but this all the dependence is actually inside the second bracket, and you take the curl of that, and what it turns out that whatever the coordinate that you work on, say partial, say the curl is if you write the curl is like the curl, if you can say use rectangular coordinates, right? So the axis, and then you have partial x, partial y, partial z, and this is jx, jy, jz, right? And all these are pi, and all these are pi. That actually doesn't matter. So you take each component, right? Say take the x component of the y, but this you consider second term. So all these say like partial x pi, partial x pi, would becomes jy. Just the second argument. We respect the argument, so that has the component just partial jy, partial t pi, and then partial is absolute value, partial x pi. Okay, and now this one you cannot directly use that, but there's another way to calculate that, just using the definition of this absolute value. The absolute value is just like x minus x pi squared plus y minus y pi squared, g minus c pi squared. Right. Let's take the derivative over with respect to x pi. That give you 1/2. This is 1/2 factor, 1/2 power, and then divided by exactly the same square root function, and take the derivative over the x pi. So we have 2 of x minus x pi, but then we have a minus 1. We take the derivative 2 of this, and then take the derivative over x minus x pi, give it minus 1. So basically cancel that. This becomes x pi minus x, or minus of this. But this ddt actually has, actually I forgot this. ddt, there's a minus sign. This minus sign. This minus sign can cancel with this minus. Right. So this is equals to this. Also to 1 constant t and then x minus pi over the square root, which is r. Okay. So each of these derivative actually change the time derivative, and then instead of taking derivative, your component divided by r. Okay. So this derivative is basically, you can say that this becomes derivative with factor t, and this becomes x minus x pi, this becomes y minus y pi, this becomes z minus z pi. So basically, it's this becomes this is the R unit vector. We calculate the full, all the component. So this is, instead of a curl, becomes a cross product. So it's basically cross product cross partial t product, and then take the retarded. Okay. So again, you can get the Jackson 6.54 by putting it the other direction. So Jackson has this in the left hand side. This one equals to this one, and minus this term. But Jackson has the order reverse. When you put it to the other side, instead of a negative sign, you reverse the order of these two guys. Okay, so it's exactly the same. All right, so you can use that and then move all this bracket out of the retarded, all this derivative out of the retarded bracket, and also actually make it more complicated because you're actually getting all the dtt partial t prime terms. And one more thing you can do is move all these partial t prime outside of the bracket again, and that is actually trivial because if you have just work on one of these. Actually, they are row and they are also retarded. T prime also, if you have that depends on x pi and t pi, but inside the retarded bracket, which means you work on this is taking the derivative with respect to this one, to and then take the retarded retarded bracket, and we can consider another, or you can take it doing another way around. If you pull it out, after you pull it out, it's not depends on x t pi, not depends on t pi. You move the t derivative out, you are not getting t pi out. Because after you do the retarded bracket, there's no t pi. T pi changes to t minus x minus x prime over c. So once you evaluate the retarded bracket, that becomes this one. There's no t pi, only t, so it becomes a ddt. Right? And obviously, that is the same as this. What they could do a derivative with respect to the second argument, and then take a derivative of the second argument with respect to t, but that is just one because there's no t here. The second argument has no t in the second term, so the derivative of second argument with respect to t is just one. So you only have the partial t pi, which is second argument, inside the retarded bracket, which is exactly this guy. Okay, so these two are the same. All right, so you can move whatever you have the t pi in the within the bracket, you move it outside. So when you move it outside, you change t pi to t. That is actually pretty straightforward, right? So now you have all the rule, and you can move this all this derivative out of the bracket, and that Jackson didn't have that written down, but that can be quite straightforward. And the reason why you do that is we want to apply it to a situation for a point charge, right? A point charge is just you have a charge just moving around Q, and that over a trajectory, so we call it R as a function of T. This is Jackson called R sub 0. I think R sub 0. I mean, just to differentiate with the, I mean, they just separate, distinguish from the radial vector. Okay, so so this is a trajectory. So for a point charge, and we know the charge density and current density are functions. Talked about that many times. You still remember that? So the charge density, what is that? Q times what? Delta function, right? Yeah, delta function. And the position is R0 as a function of T. So this is the charge density. And likewise, J current density, that's simply Q times the velocity. The velocity is simply dt. And at the same location, same delta function. Okay, so that is the rho and J. Now, this rho and J you can put in the formula and perform the integration because you have delta function. These are three-dimensional delta function. So this three-dimensional integration is trivial in the sense that wherever you see x, you just substitute into R sub 0. But that is easy, except that the original formula have gradient inside. Okay? If you have gradient inside, so first you change all this to pi, x pi and t pi. This is x pi and t pi. Okay? And then you take the derivative. Then you find that yourself get into a problem that you want to take the derivative over delta function, which is a little tricky. It's not impossible to do, but it's more tricky to do that. You get into delta pi, the derivative of delta function. Delta function is always singular, and you take another derivative is taking a derivative of a singular function. That I mean that you need some interpretation actually do that, and so it's conceptually easier to move the derivative outside, because once you take the derivative outside, you can evaluate delta function first. That make it much easier, right? So that is and then so if you apply that to this, so first you change that to using all this rule, including that the final formula, and then start from 655 to 56. Then you can divide 658 and 59, although the derivation will be pretty long. Right. So Jackson didn't show that. we probably don't want to struggle with that because, I mean, this the exam will not ask you to define that. This is a long derivation to get to this point. Okay, but it can be done. The steps are just what I said we will do. Right. So um, so that's one set of equation, and so now you have the equation. So it's you get basically that allow you to get rid of the integration. So it's no longer an integration as long as you have this R sub 0. Then in principle you can calculate that without now. This is a formula rather than integral, or it's perform the integral, except that there's a conceptual problem that this substitution of retarded actually change. So whatever the retarded bracket in 658 and 59 means, so whatever the quantity inside the retarded bracket, so you have many quantities, say, in 658, 59, say, they're all inside the retarded bracket. Yeah. Many quantities, the same thing apply. So that so originally the retarded bracket is whatever that depends on x pi and t pi. Then you change t pi to t minus this this capital R divided by c. But in this two equation, actually R pi is integrated out. There's no R pi, right? So what this means is actually changed. So originally, this is just R is just x minus x prime, right? Retarded. Right. Originally, there's no x pi, so basically you do nothing. If the original over this retarded bracket, but in this new formula applied for point charge, that actually changed because this x prime becomes the position. This actually x prime changed because remember that we have this delta x minus r sub 0, right? So when you and then this change the x prime when you put in the integral. So this is change the x prime. So wherever you see x prime actually change the r sub 0, and then this becomes c prime. So supposedly this is r sub 0. And so t prime, but t prime is not interpreted by simply t prime. Originally t prime is t minus x prime over c. It's not simply substitute this in the form of that, because now then you do that, then there's a x prime here. X prime you need to change it to r sub 0, right? And so you get r sub 0 that depends on t prime, but the t prime is t minus x minus r sub 0. There's another r sub 0 here. If you just write it down, you're not writing the solution. The solution is not yet done because you still have this r sub 0. That also depends on t pi. So you have a integrate infinite loop over there, right? Because that also depends on t pi. If you just by direct substitute this, and then you are not writing down this. What actually happened is that you need to solve this part. You need to solve this as an equation for t pi, right? As a function of x and t. That you need to solve that equation. This becomes an equation rather than expression, because there's t pi here. There's a t pi in this this trajectory of the particle. So you need to solve for t pi as a function of x and t. So given an x and t, they solve for t pi, especially the retarded. This is called the retarded time. So the 6.5558 actually this retarded bracket means you evaluate at the retarded time. So x minus r sub 0 vector, which is given, this structure assuming is given that as a function of t pi, but you evaluate that as what we call the retarded time. Okay, but the retarded time need to be solved by this equation. Okay, it's an implicit solution. Implicit equation, you have t pi here, and then there's a t pi in the r sub 0 trajectory. So given the r sub 0 trajectory, and obviously x and t, then you solve for the t pi. Okay, you solve for t pi, and that is the retarded time for a given x and t. Right? So retarded time would be a function of x and t, and then you substitute back to here, and that allow you to evaluate the bracket. Okay, so that's a process that not necessarily easy to done. So this implicit solution, implicit equations, or the solution may or may not be easy to find. Obviously, sometimes you need to solve it numerically. For analytic solution, only very simple cases you can solve for analytic solutions. And two of them I give in homework. In homework, we have a practice to solve the retarded time. Okay, so and the physically or graphically, you can let me draw maybe here. Hopefully enough to see. You can draw the space-time diagram. Again, space-time diagram, you have t over here and x, right? And so given the r sub 0 means this is we have a curl in the space-time diagram. So that's the trajectory. This is r sub 0 as a function of t. Okay. Now the process of finding retarded time is first we fix the x and t. So you choose x and t here, say whatever you choose a space-time point. You have space and time in one point. And now the retarded time is this is a backward light cone. So you draw a light cone at 45 degrees or whatever the slope is 1. And supposedly you need to put in the same dimension in order to have a slope equals to 1. So like you can put a c here, c times t. So, and this equation means that this point, given a t pi and x prime here, this light cone intersect this trajectory at this point. So this is what you call the t pi, or in this case, c t pi. Right. So this point, you need to find the intersection, the backward light cone or the retarded light cone with the trajectory that will allow you to cut. Graphically, that's what it means. Okay, so and obviously this there should be solution because the trajectory has to satisfy the property that the speed cannot be greater than the speed of light, which is the conclusion by a special relativity, which we'll go through later in the semester. But right now, you just accept that all the realistic particle has to move slower than the speed of light, meaning in this space-time diagram, the slope of this curve has to be actually in this case is always the magnitude is always greater than 1. The slope, or not always greater than 45. Right? So you can always have the intercept. Okay. So and you can also show that there will be only one intersection, right? For the retarded time, right? You won't go like quickly. because if you intersect by 2 more points, it means that this particle must go about the speed of light sometime. Otherwise, it means it catch up with the light by itself and by another way, rather than following the speed of light, the trajectory of light particle. The only thing to catch up with the light is your speed. You are moving faster. They only intersect with one point, right? But obviously, you can have another solution. If you get to the advanced solution, you can also draw a advanced light cone, and this term will be the advanced term. So remember, we are staying with the retarded solution, but we can get exactly the same equation by changing the retarded to advanced. All you need to change is this T minus, this change it to plus. That would be an advanced term. For the advanced term, you need to find this advanced, this intersection with the trajectory and the advanced light cone, the forward actually. Okay. The solution method will be pretty similar. So therefore, we will stay with the retard time and work a couple examples for that one in homework, and so you can understand that it's not easy, but for some simple cases, you can actually solve it analytically. Okay, and so that's the idea, the graphical, what this means. Okay, so get the idea how you calculate the retarded time. Okay, once you have the retarded times and all these brackets in 6.58 and 59 are just like that. So wherever you see the trajectory time r sub 0 that depends on t prime, that will be evaluated at the retarded time. Okay. So this is one set of equation, and it turns out that you can work on some transformation and change it to different form. Depends on how you like it. So Jackson, this is no, Jackson has this in the other set is 6.60 and 6.61. We have this form for E and B, and it's similar to 59 and 58 and 59, but there are some differences. You need to be a little careful to see the differences. And it turns out that this is due to Feynman. Feynman divide this expression. And I think there's a backup chapter exercise to ask you to show the equivalency of the two sets. As it turns out, it can be done, but again, it will take some work. But it can be done. I don't think we want to structure it in class. But I think I worked out the solution. And also, there's another set in chapter 14, which is in similar form, but again, very different. So in case we will not get to that because of we are behind schedule. Chapter 14, I think it's 14.2 something. 14.1 actually. So another set is 14.13 and 14.14. So we have another set of equation, expression for E and B in these two equation, chapter 14. This is called Minat-Wyckoff. I always call it Minat-Wyckoff. Some people say Minat-Wyckoff, but whatever you say it, that is fine. So they different expression. It will kind of show different 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 aspect of the solution that illustrate different physics. And so basically all of them are equivalent, although we need some work to show they are equivalent. So we have a freedom, actually have a freedom to choose which one you want to use. But again, there's 13 and 14 are more commonly used. Instead of these two sets listed in this section, although they are again they are equivalent. Okay, so that should be all from this one.